We are going to take a look now at voltaic cells. So electrical cells are cells that are adapted for scientific study, and they're also referred to as galvanic cells or voltaic cells. Now these two terms are synonymous. They're the same thing. They're all meaning electric cells that we can study and that they are spontaneous, which we'll talk about in a minute. So if you see the word galvanic cells or voltaic cells, it's all the same thing for now. So voltaic cells, I refer to them as voltaic cells, so that's how I'm going to speak of them now. So voltaic cells undergo a redox reaction in them. Okay, and essentially it's a transfer of electrons from reducing agent to the oxidizing agent. Now, in a voltaic cells, those electrons that are being transferred move in an external circuit. So we still have an oxidizing agent, we still have a reducing agent, there's still this transfer of electrons. Okay, we just see that transfer in what we consider to be an external circuit. Now, again, this is going to be just some sort of wire that's involved in our cell or our battery. Electrolytes and electrodes determine the characteristics such as voltage and current. So depending on what we have in our cell is going to change the voltage and characteristics of that cell. Okay, and what happens in different parts of a cell? So what we see is we have a cell that's connected by a porous boundary. Now this porous boundary can sometimes be sort of like a porous cup that looks something like this. So if you have your beaker, okay, essentially you just have another smaller little cup inside your beaker like this. It's not a very good drawing. Oops, I'm not making it much better here. And essentially this little cup on the inside here has a bunch of pores in it that allow some electrons, some of the electrolyte, travel through this boundary. So there's some flow of electrolyte here. Okay, we can also see this as a salt bridge. Now, we can call it a porous boundary, we can call it a salt bridge. A salt bridge generally is considered something slightly different. Same purpose. Again, if we have our two beakers here, okay, now the two beakers that I'm drawing here represent this fluid in this part of my drawing on the left here, okay, and in the other beaker it represents this fluid that would be stored in this porous boundary. Okay, now here we see that there's a very easily, we can see that there's going to be a flow of ions. Now we have to have the same thing in these two beakers, but there's definite physical separation. So we see a salt bridge that looks and is called a U-tube. Not the U-tube that you're used to, obviously, but we have a U-shaped tube that goes into each electrolyte in each beaker. Okay, it has to be exposed to the electrolyte, and essentially this is generally stuffed with some sort of cotton that is saturated with an electrolyte that allows for the movement again of electrolytes, through that U-tube. Okay, now each half cell consists of one electrode and one electrolyte. And we have a certain type of cell notation. So you'll see that we would have a half cell where we have copper and copper nitrate, and the other half cell has zinc nitrate and zinc. So let's take a look at this cell notation and what this means. So cell notation is essentially just a simplified way of expressing the cell that we are talking about. Okay, and essentially it just tells us the information of the cell without being long-winded. So in our cell notation, we always start with our anode. Okay, this is standard. Do not get this mixed up. You always have your anode on your left side and your cathode written on your right side. Now, we notate it by going an anode with a single line, electrolyte, a double line, electrolyte, a single line, our cathode. Now, you'll see here that a single line represents a phase boundary and a double line represents a physical boundary. So this single line here represents a phase boundary. Now, phase boundary means that you're dealing with something that's a solid versus, let's say, a liquid. Okay, with this double line, we have a physical boundary present, and then we have another single line, which is a phase boundary. A physical boundary would be like the separation of our two beakers that we see. Now, I like to think of this as this is our double line. There's a physical boundary, but it also kind of reminds me of the shape of our U-tube, which if I was to continue that. And that's how I like to consider that. So I like to think of this kind of as a flow of my drawing of my cell. So again, here would be an example. My anode would be listed as copper, okay? The copper electrolyte, or the electrolyte that copper is sitting in, would be copper nitrate. The physical barrier, okay, either that porous cup or my salt bridge, is going to be touching the next thing, which is the electrolyte, and the electrolyte is zinc nitrate. And then I have another phase barrier, and then I have my zinc. Okay, now this is standard cell notation. So we have anode, electrolyte, electrolyte, cathode, and we have our phase separation, our physical separation, and our phase separation in between all of those entities. So, voltaic cells are an arrangement of two half cells separated by this porous boundary. And again, this porous boundary can be a porous cup, or it can be that U-shaped tube. Okay, so a theoretical voltaic cell. What do we know about our SOA and our SRA? We have to have some sort of transfer of electrons, and we know that that transfer of electrons is between our SOA and our SRA. So we made up this little phrase to help us remember what is happening in our voltaic cells. So we came up with Anox ate a red cat. Now, some people prefer Leo a gurk. You're already familiar with Leo and Gur from our previous little section that we've done so far, and we've just add Leo a gurk. So when I went through Chemistry 30, I learned Anox ate a red cat, and that's just stuck with me. So I tend to use that one, but if you prefer Leo a gurk and that's just easier for your brain to remember, do that. That's no problem. Okay, so Anox ate a red cat. What that means is at the anode is oxidation, and at the cathode is reduction. That's all that we have to remember there. Okay, again, Leoa gurk, our oxidation at the anode, which is OA, part of that, and gurk is reduction at the cathode. Okay, now in our voltaic cell, in our electrolyte, we always have some sort of cation and anion present. Now, in our voltaic cell, cations move towards the cathode and anions move towards the anode. Electrons will move through the wire, and from our previous lesson, they always move from your anode to your cathode. Okay? So if we have an example of our silver copper cell. So essentially we need to look at silver and copper. Now when we talk about silver copper cell, we have silver solid, we have silver ions, we have copper solid, and we have copper ions present in that cell. So when we look at our data table, we need to figure out which of these entities is our SOA and which is our SRA. So let's go over to our data booklet. Even though I have it kind of listed underneath there, we're going to go through the motions. So when I take a look at my data booklet here, let's again erase these lines. I guess we can keep that one, but that's okay. So when I take a look at my data booklet here, I'm going to find my copper half reaction, which I actually had circled there. Okay, and I'm going to try to find my silver half reaction, which is listed here. So what I see is that because I have silver ions, and let me zoom in here a little bit, because I have silver ions and silver solid, and both entities are present, as well as copper ions and copper solid, and both of those entities are present, I need to determine my SOA and my SRA. Now my strongest oxidizing agent is going to be this guy at my top left, and my strongest reducing agent is going to be this guy in my bottom right. So my silver ions are my SOA, and my copper solid is my SRA. So when I go back, again, you'll see my silver ions, my SOA, and my SRA is my copper atoms, or my solid copper. Okay, so what I need to see here is that my SOA, we can't forget that our SOA is the thing that is being reduced. So our SOA undergoes reduction at the cathode, and our SRA undergoes oxidation at the anode. Cations move again towards our cathode, anions move towards our anode, and electrons move through the wire from our anode to our cathode. Now, if I was to look at this next picture, it looks very convoluted, so don't get too stressed out when you see it right away. I'm going to go through everything that we've talked about here. Okay, this is the big thing that we need to keep our eyes on right now, is labeling. We're going to go through and essentially label our silver copper cell. So when we take a look at this, we have silver sort of in this half cell, and we have copper in sort of this half cell. So what we need to do is we need to start by labeling our anode, our cathode, and our direction of our electrons and anions and cations. So the first thing that we know is we know that this reaction happens to be our SOA. Now again, SOA is reduction at our cathode. So what that tells us is that this entity, our silver ions, are being reduced at the cathode. So if I didn't have this already labeled as a cathode, I would know that the reaction happening at my cathode is going to be silver. Okay, so silver is going to be our reaction at our cathode. Now the one thing we need to make clear here is that even though a cathode is listed to be a solid entity, okay, the reaction at the cathode, okay, is the reduction of these silver ions. Now the silver ions aren't the solid itself. Your silver solid is the solid. However, the reaction at the cathode is reduction. So we're gaining electrons at that cathode. Okay, our SRA is the opposite. Okay, it's oxidation at the anode. And we know that what is oxidized is our copper, and it's turned into copper 2 and 2 electrons. So our strongest reducing agent is oxidized at our anode, and again we have our solid entity turning into copper ions and our electrons. So what we see here is that our copper on our anode side, the solid copper, is in fact the anode itself. Okay, it is the thing that is being oxidized. Now, a few things that you need to think about. If you have electrons that are being lost by our SRA, those electrons need to be transferred to our SOA. Now, in order to do that, they travel through a wire. So if you see electrons as a product, you know that this is oxidation. Okay, we're losing those electrons. We also know it's our strongest reducing agent. And those electrons are pushed out of the metal, and they are pushed into the wire, and they travel down the wire from our anode to our cathode. Okay, and again, the movement of electrons is as follows. Okay, so that's important. We've now labeled our electrons, and we just know from previous lessons and just from being an expert at this that electrons always move from the anode to the cathode. We've now labeled our cathode, okay, as a positive charge. It's the cathode, it has the reduction there, and our anode is here, negative charge, and it has the oxidation there. A few other things that we need to do is we need to identify the direction of our ion movement. So what you'll see here is positive ions, regardless of the nature of them, will move towards our cathode, or cations will move towards the cathode. So we have silver ions moving towards the cathode. We have sodium ions, which is from the salt bridge. They're not terribly important, also moving towards our our cathode. And we also see that these copper-2 ions from the other beaker are starting to migrate towards the cathode. So all of our cations move towards the cathode. Now if we look at our, let's see here, whoops. What's going on? Here we go. If we look at our other half cell and our other ions present, we see that our negative ions, such as nitrate, are moving towards our anode. So anions move towards the anode. So you'll see that they move sort of in this direction. And two other things to note. If something is being reduced, so if we look at this reduction of silver, we are gaining, we're changing the silver ions that are present in the solution, and we're transforming them into solid silver. So what we see in this beaker here on the left is we should see that there's some buildup of our silver, our solid silver, that attaches to the cathode. So we have a buildup of these silver atoms that have just now been formed from our silver ions. Now inversely, we see in the other beaker where oxidation is occurring, we're losing electrons. However, we're still transferring solid copper into an entity that has a charge. Now copper ions, when they're in solution, have a blue color. So what we see here is that this solution begins to turn blue. What we also see is that if something is losing electrons, it's going to be losing some mass. So we see that this electrode here is starting to lose some mass, and it's starting to sort of dissolve in this solution. Okay, other things that you might be able to see is that because our copper ions are moving towards our cathode, it's cations moving towards the cathode, you might see some blue that's sort of working its way up this salt bridge. Okay, so you'll see some transfer of our blue going up into that salt bridge as well. Okay, so again, with our example with our silver copper cell, we have our cell notation. Now again, we always list our anode first. So we list our anode, then our cathode in our cell notation. So our standard cell notation is going to be our copper with a phase barrier to our copper ions. Now if we think of this as traveling through that electrochemical cell, we can say if we start with this copper here, and if we go through the actual physical space in this cell, it makes sense as to why our notation is the way it is. So we start with our anode, and as we go through, we dip into our first electrolyte, which is our copper electrolyte, and then we go through our salt bridge, and we go down into our silver electrolyte, and then we go to the silver. So when we go back to our our standard cell notation, we see again our copper electrolyte. Notice that in this example, the nitrate is not listed. Nitrate is simply a spectator ion. It doesn't play a role in the reaction. So sometimes we include it as part of our electrolyte, but it doesn't need to be there. The important part is that copper ion. Okay, then we have a physical barrier as that U-shaped tube or a porous boundary. Okay, and then we have our silver electrolyte and then our solid silver. So again, we have reduction at the cathode. This again is going to be our SOA, Leoa Gurk, okay, or anox zeta red cat, okay, and this is going to be our SRA. So we see that we have to always balance the number of electrons. So in our reduction equation, we need to multiply it by 2 to get the same number of electrons transferred in our copper half reaction. So our net overall reaction is for every copper solid atom, we have to have 2 silver ions forming a single copper ion and 2 silver atoms. So for every 1 copper, essentially there's 2 silvers. Okay, so the next little section here, we know that from our data booklet, now let's just flip back over there, whoops, we know from our data booklet that we have some entities, like these are sort of basic half reactions. However, we have some entities such as our permanganate, okay, And this is one of our strongest oxidizing agents. It's permanganate and acid and electrons. Well, generally, if this whole reaction, regardless of if you're looking at the reactants or the products, doesn't have a solid phase. And what we just talked about is the fact that in our first example, there was an entity that had a solid phase in it to be our electrodes. So what about these examples? There's several of them that do not have a solid phase in the reaction. So what do we do about them when we want to use them in our cells? Now, the reason why we want to use them in our cells is because they are such good oxidizing agents or reducing agents. We want to be efficient in what we're producing so we can create a better cell by using something like this. So let's take a look at how we do that and what that maybe means. So what if your SOA or our SRA are not the electrode? So we can talk about the acid dichromate and copper cell. In that case, we use what we call an inert electrode. Okay, this electrode is unreactive. It doesn't play a part in the reaction, but it generally just provides a location for that reaction to occur. So it's a little bit conductive, but it will not be part of that reaction. Now, carbon and platinum are common inert electrodes that we see. Generally, in Chemistry 30, we will be using carbon electrodes because they are quite a bit cheaper than our platinum, obviously. So we see that we use carbon quite frequently, or graphite of some kind, to see these reactions occur. So if we look at our example, we have our iron dichromate. Is this the reaction that I said? Oh, not quite. So we have our acid dichromate. This should have acid in it as well. Okay, and we have two inert electrodes. We're dealing with our carbon. So what we need to see is we need to look at our data booklet and see what our two half reactions are going to be for this cell. So we jump back over to our chemistry data booklet. We take a look. I'm just going to, again, erase some of the mess that I've made here. So when we take a look at our data booklet, we're looking for acid dichromate, which is what we see here, acid dichromate. Okay, and we also see that we need our iron half cell. Now notice in the example, there's no solid component of iron. Oops. Let me make that a little bit less messy. Okay, so we're dealing with this half reaction, our Fe3 and our Fe2. Now notice that this will be our SRA and this will be our SOA. So our SOA undergoes reduction at the cathode and our SRA undergoes oxidation at the anode. So I always write down my oxidation half reaction and my reduction half reaction. And I always write down that this is my SRA and that this is my SOA. So my SRA, again, is that Fe2 positive. And I always write it from right to left. I read it from left to right, but I need to write it the other way. Okay, and my SOA is my dichromate half reaction, which is, I just have a paper here with it on it, so I don't need to flip back. Cr2O7 2 minus plus 14 hydrogens plus 6 electrons gives us 2 chromium ions and 7 water molecules. Okay. So here are our two half reactions. Again, our reduction half reaction and our oxidation half reaction. Now, this is our standard cell notation. Notice that our anode and our cathode, our two electrodes, are both carbon. They're both inert electrodes. That's no problem. All this tells us is that we have our electrolytes as being our SOA and our SRA. So when we solve for our net reaction here, I'm just going to choose a different color. When we solve for our net reaction, again, we always need to make sure our electrons are balanced. So when I go through, I need to multiply this guy by 6 in order to get a balanced half reaction. So we have 6 iron 2 ions. And again, we have 6 iron 3 ions. Okay, so there's our net chemical reaction. Again, we've listed this as the SRA, this as the SOA reduction. Okay, now remember, reduction is at the cathode and oxidation is at the anode. Now, electrons are going to flow from our anode to our cathode. Okay, so if I was to draw that in a wire, I would see my electrons moving anode to cathode. I would note that my positive ions are moving towards my cathode, okay, which is where this reaction is undergoing, and my negative ions are moving towards my anode. Now this is a little bit weird of an example, and you're definitely going to need to try another one to get the hang of that. So there's some practice questions in the textbook that I would definitely recommend going to check out before you go on to the assignment. At any point, if you need to go back, take notes, slow it down, and rewind, definitely do that now, and good luck.